Hi there, we continue to learn how this Chip-8 computer work and how all the computers work. So we discussed the main components of any computer. So it's a CPU, this is memory, input device, output device. But let's talk more about like how do they communicate together, how do they interact. So first of all, like memory contains programs, which are instructions and data. This is the modern architecture where we store everything in the same place, and any memory contain instructions and data, and they're all intermixed. And so program is basically a sequence of CPU instructions that say to CPU what it needs to do, and also some data to process. In our case, for instance, for this Chip-8 computer, we use sprites. We can also use some text messages so that are stored in this program. Like, for instance, if we wanted to show hello world, we need to store it somewhere inside the program, and this is going to be example of program data. And instructions gonna say to the CPU, please take it from this memory area and put it in the registers, then put it into the other part of memory, and then give command to the display to show that. And so CPU basically communicates with memory and sending commands just to read that and store something, and to store and to read. And also it communicates with input and output devices. So for output devices, as a display here, we just send commands, just draw something at some place on the screen. Clear screen also, and for input device it tracks the keys that were the key downs on the keyboard when the keys that were pressed, and saves that also in internal memory. And then program is the one that says what to do with that, what routine to subroutine to call, or function to call to process that, or to draw something, and so on. And for CPU itself, as a real like silicon CPUs, they have a built-in memory that starts from registers, and in this case we have 16 so-called V registers. They have their special name V registers, and also there is an index register that is named by I. And also in every computer we have a program counter. So this is the counter where a CPU saves the address at which it operates right now, and where it needs to get the new instruction. And also with the like branching commands, like all we know in JavaScript, like we have else, if else statements, with using which we can just change the flow of our program. And on the level of the CPU, this changes the program counter. So depending on the branch, we can jump to specific location, and also we can get back if we return from function, for instance. Yeah, it's also used for calling functions and getting back from them. Stack, it's also classical data structure that are widely used in all our programs and computers, also on this computer level. And this is used to save the return address. First of all, to return address of the function when it's called, and whenever we see return statement in the function itself, we know where exactly we should go. And as it's stack, it can stack many items inside, and whenever we have like many calls, and so we can get back to the original function. So it doesn't matter how deep we're gonna go, it's just limited by the size of the stack, and in this case we just go further and further, and can invoke many functions. But also, like, and you remember maybe sometimes you can see like Stack Overflow have a famous website with that like error. It means like, yeah, that the invocation of functions was there's so many functions invoked, and so it doesn't fit the memory anymore allowed for the stack. And also this specific implementation of the Chip-8 computer system, I would say it's a delay timer and sound timer that are used to generate sounds. I don't do it like right now here in this specific code, But anyway, it's a delay timer is needed for any kind of animation because you need to sync with real time. And sound timer, it's needed to have some sounds available. Right now it's not used, but anyway, in this reference implementation, this just every cycle we just update these values. So it's a kind of a wrap up of the architecture itself, of the virtual machine, of its big part. And also next we're gonna check two key things that are left is memory organization, its size and how it's organized, and also instruction set. This is key in this first version of first implementation. So Chip-8 memory, it's 4 kilobytes. It's just a tiny memory, because typically like your computer probably have some 4 GB or 8, 16 gigabytes, which is like we have kilobytes, megabytes, and then gigabytes. So it's like it's a million times less than you have in your computer. And that is enough for simple apps, just to show how computers work. And so, and also what is really necessary to know when we play with the kind of a low-level systems like this is using hexadecimal system, because it's much easier to write commands and understand what's happening inside because of the format. For instance, like here we have 4 kilobytes of RAM. It means like we have 1000, it's in hex. And what it means on practice, that all addresses that we have there just stick to 3 digits. This is the main fact that you should know for this system, that whenever you have an address in the system, it's not bigger than 3 digits, 3 positions. So it's like 000 up to FFF, which in decimal means 15. And this is good. You're gonna see that in instruction set. For instance, whenever we encode something like this, XXX means pretty much any address, and it fits just in 3 digits, and that's really good for the system. But for the memory itself, the two key things, since pretty much in every computer like it is like that, we have some system memory that sometimes in real computers it is also organized as a read-only memory with some bias inside, so basic input-output system that just handles the basic things to check up computer whenever it was turned on, and some basic manipulations with hardware. But also here, like we, for instance, have font set, so it's located at 50, and we just store all the like numbers from 0 to 9, and also letters from A to F. And this is needed. You need to know that in order to draw some letter, because it's already in this reference implementation. So you can use this font set as sprites to draw it on the screen. And this is what I've done in my demo for drawing these numbers from 0 to 5. And the second part is the programs memory space. So it is it's not definitely 2FF, it's FFF. I can use all of the space here. I'm gonna fix that. So it's instructions and data, you can locate it, but in the same in this space. But basically, it is located 200. Why it's needed to? Why do you need to know? It's you need to know that because the entry point is 200. This is where your program starts, and whenever you want to get back to the first instruction, so it's 200, and I use it like to create an infinite loop in order to start over and over again. And you see this numbers from 0 to 5 that just keep on looping in the big loop. But let's just take a look at the instruction set of this machine, and you're gonna see this word opcode, and this is quite popular in computing, and you can see it quite often, and it just basically means operation code. So any operation here is, in instruction, it's also like the synonym of this is operation, and in the computer, it's just have some code So this is the also we can talk learn more this just like if we go deeper in like inside the CPU, or like the concept of any computing system, I would say. So whenever you want to have some operations to perform, you need to assign some code. It's like all this coding start, for instance, even if you code like symbols with the Morse code, whenever like you have also the symbols on the screen like with the ASCII code, and also the same here. Just if you want to perform some operation, you need to have some numerical value assigned to it as a code, because everything here in the computer, it's like it's a binary and it's numbers and at the end. And so every CPU like this one, like or Intel's or Nvidia's or whatever, they have their own instruction set and operation code for every instruction. And so the low-level programmers, they typically learn that and can write low-level programs using these codes, but the higher level languages, they just use compilers that just can translate whatever you've written in just Python or like C, C++ to this instruction set. And in our case, we have 2 bytes instructions, so the length of the instruction is 2 bytes, like as a sequence of 2 bytes. And so pretty much they're denoted here like as 4x. And the first implementation, the first one that allows you to draw something on the screen, uses just 3 types of these instructions. So first it's a data manipulation. The second is like everything related to flow control, and the third group is display level, so output device related. So it's display here. We don't use any other stuff here, no keyboard, no other complex things, but we just gonna extend that in the next videos, I would say, but just not to lose in this many details right now. Just we're gonna focus on 3 of them. All this data manipulation is really similar to what we have in all our computers. So basically what we can do, for instance, what are the ones that are implemented. So for instance, what does it mean? 6xkk, it means like the command, like the first it should start, the first digit should be 6, and the second digit it denotes the number of the register. We have 16 of them, so we can have x can be something from 0 to 15, so 16 registers, and it would denote the number of the register where we want to write. This kk, it means just the value we want to put there, and so it's like just 1 byte. It can be something from 0 to 255. And so with this command, we just can assign something like that to the register. The commands that opcodes that starts from 7, they add some value to like kk, this something in between 0 and 255 to the current value of the register vx. And the third one is used here to address the drawing, the location of the sprite that we want to draw. It's just set in the index register, and it can use the whole 3 digits, so pretty much the ones that we need here to address all the memory that we have. And so it starts with A and then goes the address, so it's just quite simple. The second group is flow control, so it's a branching in subroutines, 2 main things where you can change the flow. So first it's a jump to address, also 3x means just pretty much you prefix any address with the number 1 and you get the instruction that jumps to this address. The second is 2 starts for the calling subroutine located at some address, and just pretty much any address. The return from subroutine is just classical return function. So it's you just code it with the double zeros and EE, and also some branching instruction that is example that is starts from 3. The X goes also stands for the number of of this register that we use, and the KK, the value that we want to check. So it can help you to organize loops, for instance, one of the keys of any program. And display the signature of the display function. I'm gonna explain it just in a minute. So first of all, we just need the function to clear our screen. So it's just quite simple, just some command we need to just write down and use in our code. And for instance, drawing something at Vx, Vy, pretty much encoded by the second and the third digit in this 4-digit commands. First digit here is D, that encodes the command itself. And also, it's by default, it's every time width of 5 pixels and height of n. That is encoded by the last digit in this command. So in our case, we use the height of 5. This is the height of these symbols that we have. And that's pretty much main thing that you need to know in order to follow the code in JavaScript itself, to give you an understanding of what we are coding and why we are coding it and how it relates to the systems that you know. And in general, it can give you a good overview of the computing itself and help you to build fundamentals of computing. And see you in the next video, where we just walk through the JavaScript code and check how we can update it in the future. Bye.